So, good morning, everybody. So, it's a great pleasure to have Hirohiko Shimada today, who is going to talk about RG flows in replica coupled conformal field theories. So, please, Hirohiko.
So, thank you very much, Jesper, for introduction. And I would like to thank all the organizers to giving me this opportunity to talk about this. So I will talk about this replica coupled CFT and its RG flows. So typical Hamiltonian for the three replicas looks like this. Actually, I start with disordered models also. So in this workshop, I think we had already great talk by Ilya Grutzberg and Martin Gilbauer about random systems. But I will talk about how to say, mainly about the disordered magnetic systems like ON and spin systems. And I also talk about the unitary case. So let me continue. So as we all know, so after VZ, we have very good control about 2D CFTs in general. But still, even in 2D, the CFTs for these sort of systems are very difficult in many ways. So here I do some diagram. So here we have well-known interminimal models, 3-state pots and Ising. So all the others are okay. So non-unitary difficult problem. So here we have this very difficult CFTs for these sort of systems. And we also have this Q-state pots and ON and ZK parafermions for generic non-integer n. Yeah, these are also non-unitary systems. So especially for this part, because this sort of system has some effective symmetries of replica or supergroup symmetry. So in order to understand this difficult, so that's CFTs for disordered systems, I think we need deep understanding of these symmetries. Okay, so this replica part. So replica symmetry comes from this replica trick. So as we all know, this replica symmetry comes from this identity. So we use this identity, we use this M0 limit to compute disordered average for free energies. And M denotes the number of replicas here. Okay, so on top of this diagram, I superpose this. So M equals 0 describes disordered models. And also for here in the unitary region, we have a series of replica CFTs. So from M equals infinity to 3 and 2 and 1. So 1 is the original usual CFT. Okay. So here I list two unsolved problems, outstanding ones. So these are the CFTs at M equals 0. These are very interesting, especially it has non-perturbative fixed point. And I think this is very important in view of immersion group. Now, the other is this M-coupled Q-state pots model. So for Q equals 3 or 4, these are unitary. And we have series of CFTs for M equals 3, 4, 5, and so on. So the typical CFTs are like this. So 3-set pots model CFT with an S4 extended symmetry if M equals 4. So it can be a Bootstat targets. It's unitary. Okay, so but let me start with this M equals 0 part because it's easier to introduce him. So in order to explore this RG landscape, useful analytical tools are this. So Epsilon-expansion around the Ising model. So we fix the dimension d equal 2 in this talk. and changes the, let's say, the size of internal symmetries, N of ON or Q of Q set points. So in 2D2, actually, this coupled Ising model saturates so-called the Harris criterion. So the effective coupling of this form, energy-energy coupling, becomes marginal at the Ising point. That's actually N equal 1 or Q equal 2. And randomness is relevant if this 2 minus 2 delta energy operator. So in this case, we may have a non-trivial fixed point for the random system. So this idea is introduced, I think, by Ludwig in this paper. For this Q minus 2 expansion is introduced. And the schematic beta function takes this form at one loop order. So it starts with linear term epsilon g, and the coefficient of g square is given by m minus 2. So this is diagram counting, and plus c square, and here c is the structure constant for energy operators. And in Potts model in 2D, this c square vanishes because of self-duality of the Potts model in 2D. Okay, so in that case, we have this schematic beta function. So if we plot this, if m is less than 2, it looks like this convex thing. And we have infrared fixed point in G positive region, G star. So this corresponds to the disordered CFTs. And if m is larger than 2, we have infrared fixed point in negative region, and this corresponds to the unitary m equals 3, 4, 5 cases. And it is known that m equal 2, and so m equal 2, at m equal 2, we have Ashkin-Taylor models at q equal 2. But if q is larger than 2, it is known that so even in such models, generic q is integrable and actually found to be massive. So we discuss it basically m equals 3, 4, 5 as an isolated fixed point. Okay. So let me start with this ON thing, ON models. So ON model has this famous geometric representation. So this is a linearized Boltzmann weight, and this mu is the measures for spins for that lives on Sn minus 1. And so this measure satisfies this part, and so this pattern function has this final form. So x is the weight for the bond, occupied bond, and n is the weight, non-local weight for the loops, for one loops. And it becomes particularly simple on honeycomb lattice, it is known. So actually, it has a critical point at the special values of xt, given by this formula in n. And the point is that around this critical point, this operator, SISJ squared, is irrelevant in energy. So it's critical. And it is also true that this linearized action is the same as exponential action, because these operators are irrelevant. Okay. So now the models with quench disorder is simply defined in this form. So now x depends on the link to link. It respects some distribution function like this. So it's a dilute case. I mean, with probability p, it takes some strong bond, and with probability 1 minus 1, it takes a weak bond. Okay, so I think the next step. So in order to analyze this, we use this Replica trick, celebrated Replica trick. So by this, we will obtain the models that couples between the data has interlayer coupling in replicas, but horizontally homogeneous. Okay, so if we take the continuum limit of this model in ON in general, so it looks like this. So action looks like this. This CFT action plus temperature fluctuations. So X is the position, and okay, so corresponds to the link positions. Now, if we consider the disordered models, this M depends on the position, and we will take the disordered average using this, let's say, Gaussian distribution case. Then the average of Z is M yields this effective action. So this D0 is the so variance of this Gaussian, and we have here the coupling. In general, we have this higher composite operators, but in the ON model, energy operator is identified with 1,3 operator, so I use this vertex operator. And okay, so N is parameterized by this formula with this -2 cosine pi over alpha minus square. Okay. So the phi of this vertex operator comes from this lattice height function. Okay. Now we use this identification. So bond is normalized to energy operator that is actually 1,3, yeah, 1,3 operator. So I think this plot is important. For the ON model, the dimension of this energy operator is less than 1, below n equal 1. So this effect coupling becomes, excuse me, slightly relevant here. If n is less than 1, yeah, it becomes slightly relevant. And these higher composite operator terms becomes very relevant. Okay. Actually, this horizontal axis is proportional to this parameter rho. That is also proportional to the kappa of SLE. Okay. So because of this operator dimensions behavior, here we may have disordered critical point. So if I do this, we get this horizontally homogeneous models. And so actually we use this behavior of operator product expansion. So intuitive interpretation of this OPE, energy OPE, is that if we these two bonds approaches, it can create loop. So this loop contributes to the free energy, and if this makes energy operator again, then this shifts the TC. And this C of structure constant of energy operator encodes some important selection rules. So at n equal 1, because it is the critical point is self-dual, it satisfies Cramer's linearity. So this 3-point function squared becomes 0. And if n approaches 0, actually this structure constant has a pole at n equals 0 and diverges. So this means actually repulsion between these energy operator bonds at this is the effect of this repulsion, because this loop is highly suppressed at n equals 0. So relatively this contribution of energy operator dominates.
Can you explain why there are these poles at this point? I don't understand. How did you derive this formula?
Okay, so this formula is derived by Coulomb-Gas method. So actually, so energy operator in the ON model is degenerate at level 3. So we can compute epsilon, epsilon, sigma, sigma, for instance.
But that's for a single ON model, I understand. But now,
okay, so
you have several models, you put them together, and somehow you get a pole.
Okay,
that's what I don't understand.
This C of epsilon, epsilon, epsilon is that of single ON model that appears in the beta function, that enters in the beta function, this C square. So we consider the perturbation theory around the single ON model. So,
okay, I understand. N here refers to ON model. It's not the number of copies. Yeah. Okay. Sorry about that.
Okay, good. So intuitively, this pole is understood by this strong repulsion at n equals 0. Yeah, because it's a ratio between this contribution loop and this bond. Actually, this has an important consequence in the RG flow. So schematic RG flow looks like this. Below n equals 1, it can create weak coupling random fixed point. But if it approaches to n equals 0, it, run away to infinite strength, infinite disorder strength. So below that, intuitively, these replicas are strongly coupled in the vertical direction. And the intuitive picture is that the number of closed loop is small. So interior hopping dominates the system. So it's strongly coupling in this direction.
And so can I ask a question?
May I ask a question?
Yes.
I was just wondering, this picture is for which value of big M?
Excuse me. So this is about m equals 0. I start with m equals 0. M equals 0. So I discuss both m equals 0 and m equals 3, 4, 5, and now in the m equals 0 part.
I'm confused at what you're doing, because if you look at self-avoiding polymers, the coupling is repulsive. If you look at the disordered system, the coupling is attractive. So about what are you talking? Loop-arised random walk is repulsive. The disordered system at n equals 0 is attractive.
Well,
so what is the sign of your G0?
Yeah, so G0 is now positive, I think.
So then it's a disordered model, and it has nothing to do with self-avoiding walks or loop-arised random walks. It's the opposite sign of the coupling.
You are talking about this effective coupling, sign of effective coupling.
G0.
Yeah, G0.
All right, if it's positive and with the signs you have on the top of your slide, then it's a disordered system.
Yeah, it's about
it has nothing to do with self-avoiding polymers. It's opposite sign of self-avoiding polymers and the opposite sign of loop-arised random walks.
Loop-based random walk you are talking about. So forget about loops. I'm not considering loop-erased random walk. So n equals 0 is the usual self-avoiding walk.
But there's a fixed point at finite G and it's stable. It's not at infinity.
But Kai, I think so we take first ON model, and now we are making this disordered. So, for example, n equals 0 self-avoiding walk. And
it's
then,
not disordered. I mean, it's a positive coupling. Now we agree.
But here this RG flow arises from taking this model and making it disordered in addition, because there's this M, which is the number of disordered copies. So it's kind of disordered self-avoiding. So this G0 coupling is not the coupling that you are thinking about, because you are thinking about the 5⁴ coupling, but that coupling is already like taken into account by the CFT description. So now this G0 is a completely different coupling. It has nothing to do with this 5⁴ coupling that you're thinking about.
Also, M is the replicas.
M is the replicas.
Yeah, it's an attempt to describe two-dimensional polymers in a disordered environment.
Okay. So sorry, I missed the second coupling one.
Yeah.
Coupling replica index. Okay, sorry.
Okay, I think maybe this is clear now.
I see. Okay, G0 is coupling for this energy. Okay.
But why are you excluding the part on the left side of this pole?
Looks like this part, but so later it becomes clear this part. What this means. Yeah.
Okay.
Okay. So yeah, this is how to compute beta function. Okay. So the dimensions, unmasked dimensions of energy beta and spin beta. So it contains also the diagram for 4-point function. This is basically ER space minimization group computation. So testing one. And okay, so here is the result for the unmasked dimensions for the spin operator. So if this fixed point persists at n equals 0, it is like 8% of the original spin dimensions. Okay, so actually, so the same type of computation is known also for the Q state, disordered Q state Potts model. And there also this dimension correction is known. And somehow the coefficient is very interesting values. And somehow ON model corresponds to some recursion times for the body center cubic lattices. And in the case of Potts, it's like given by recursion times of face-centered cubic lattice. It's the same as lattice Green's functions, value of lattice Green's function somehow. So in the case of Potts models, this energy-energy couplings becomes relevant if Q is larger than 2 here, because the energy operator in Potts model is given by 2-1 operator. So if I plot the dimensions, it becomes less than 1 when Q is larger than 2. And here, by Cardi and Jesper-Jacobsen, this theoretical prediction is this dot dashed line, and these dots are numerical prediction, and it agrees perfectly around Q equals 3 and Q equals 3.5 and something like 4. Okay, now we talk about this C theorem. So general C theorem for unitary systems says that the beta function is the gradient of some C function, and with some visual convention, it looks like this. But for this coupled case, this part, so-called Zamolodchikov metric, is given by this 2-point function of this perturbing field, and it is proportional to m times m minus 1. So this changes its sign below m equal 1. So actually, RG flow has some uphill direction, and it goes uphill direction. So this metric has some negative eigenvalue, contains negative eigenvalue. So in that direction, RG flow becomes uphill. So central charge actually increases along the flow in the randomness direction. This peculiar thing happens. So
and maybe here we
yes.
should make sure that we are talking about the effective central charge. So when we're talking about the disordered model, it's the derivative with respect to replicas evaluated at 0.
Yeah, indeed. So I listed this formula here. Thanks for the explanation. So this effective central charge is very physical one. So it appears in the finite correction of the average free energies. Yeah. And theoretically, it can be computed by the derivative at m equals 0 of Cm. Okay. But okay, so these are very physical one, and we can indeed extract from the computation of by transfer matrix, for instance. So we do we multiply random transfer matrix many times, like 10 to the 7th in this direction. And okay, so this.
Sorry, I'm confused somehow. I
please.
always thought that the free energy at in the limit, when m is the number of replicas is 0, is strictly equal to 0, just by definition of the replica limit. So it has no finite size corrections. For that reason, the C equals 0 for the series, the usual C, not the effective C. But I don't think it has any corrections. It should not have any corrections because it's 1 in any finite system, any size, the partition function. So where do you get the finite size corrections from?
So I think directly at m equals 0, it's z equals 1, but actually physical things is encoded in the derivative at m equals 0.
No, I'm not asking if there is such a thing as the derivative. The derivative is fine. I'm claiming that the free energy cannot have finite size corrections. That's what I'm claiming. So whatever your CF, it cannot be related to finite size corrections to free energy.
Okay, well, so in this disordered ON model, for instance, we have actually finite size correction that we can measure. So we can compute free energy per area by multiplying these transfer matrices, and we can take this average over 10 to the cubed 1000 realization, and it has finite size correction.
So this average free energy, it's measured in the transfer matrix formalism by from the Lyapunov exponent of this product of random matrices. And it couples, it's shown here in the box, it couples to the effective central charge. This was discussed in my thesis a long time ago, maybe even before. So there are indeed finite size corrections, and it's those finite size corrections that are used to measure this effective central charge. So
yes, sir. Sorry. Again, where is it coming from? So the formalism is set up in a way.
Can I explain?
Yeah.
Well, it's because there was a log z before. So in order to extract log z, you have to take the derivative with respect to n. So indeed, of the replicated theory, which you take strictly at n equals 0, that replicated theory will have z equals 0. But for this particular observable, the free energy of the replicated theory is not the physical free energy that you're interested in. The physical free energy has to be extracted as derivative.
Oh, I see. This is okay. I see what you're saying. Yes. Okay. Fine. Thank you.
So using this effective central charge, actually RG flow can be extracted. And it looks like this. It's very rich. So along this axis, we have, we have fixed the point of pure models. So this is dilute critical point and dense critical point, and this is zero temperature fully packed fixed point. On top of that, we have these randomness directions. And indeed, we have random critical point here in the uphill direction. But on top of that, actually, we found the strong disordered fixed point here. This is actually multicritical, maybe tricritical in this sense. It has two unstable directions. So, for instance, along this randomness trajectory, we have P and R and S and okay, so zero temperature fixed point here. So along this curve, we have this configuration. So we goes up and actually we find this strong coupling fixed here. And I think this existence of this strong coupling is very interesting and perhaps important. So this diagram is for n equal 0.6. Okay, so now the previous schematic diagram looks like this, but now we find the real configuration is like this. So up to some value of small n, like 0.5, we have this weak coupling fixed point. But actually, this trajectory turns and it is continued as strong disordered random fixed point. Okay, so this plot is for the increase of central charge to pure to this weak randomness fixed point. This is confirmed very well. I mean, this dashed line is theoretical prediction, and this is a measurement. So this corresponds to basically this. Yes.
So how did you get this this phase diagram? What kind of computation did you do to discover this multicritical fixed point?
This was found by transfer matrix, numerically found. So if it has extremal value, it might correspond to a fixed point. And okay, so this configuration corresponds to this situation for n equal 0.6, for instance.
Well,
so this is
it's kind of the synthesis of many different n values where you can do these numerical computations. So the previous slide shows one for 0.6.
Yes.
Where you can see that you're going to intersect two non-trivial fixed points. And then if you do it for a smaller n, like 0.3, for example,
Yes, yeah.
then you are going to see that this effect of encountering these two fixed points will go away. And it's all summarized in this diagram here.
Yeah. And indeed, we can show these branches cannot be found in field theory, at least at some level of conformal perturbation theory. So actually, so this strong disordered fixed point also exists for n equal 1. Okay, in a random bond Ising case. So random bond Ising case actually is naively speaking, it's marginally irrelevant because coefficient of this square is minus. And here we have some logarithmic CFT, but on top of that we have this strongly disordered fixed point. So at n equal 1, this random bond Ising model is equivalent to M-coupled model at n equals 0. And we can do some Borel-Pade analysis on these beta functions at no order by Gracie. And we found that every Borel-Pade scheme, there is some critical value m, and below which we have no implied fixed point. So this is.
There is or there is not? I missed the claim.
So I do the possible Borel-Pade scheme, for instance, 3, 1, 2, 2, and 1, 3. But for every combination of this Borel-Pade analysis, this infinite fixed point disappears. I mean, so this, okay, beta function may have some such fictitious, how to say, infinite fixed point with these cubed and G4 term. But if we do Borel-Pade analysis, it disappears.
So you're talking about m equals 0 limit, or you're talking for m?
Yeah, so m equals
0
is contained in that limit. Okay, so this at n equal 1. Okay, so at random from Ising model case, this beta function is known for general M, and we can do the analysis for generic M. But if M is below something like 2.75, this infinite fixed point disappears. I mean, fixed point with positive coupling disappears.
So this means that the phase diagram changes, right? I mean, this the whole red line disappears.
This means this multicritical point is really non-perturbative. I mean, in a perturbative RG, we cannot find this. That's okay. Very, how to say, crude argument, but that's is that direction discussion, that direction of argument. So this is cannot be found in the conformal perturbation theory.
And what do you know about this fixed point? You know its center of charge. You know, what do you know about it?
Yes, that's the point. I think we know the center of charge. I mean, numerically. Yeah.
And also, I mean, since you did transfer matrix, I guess you also know some operator
some
dimensions.
Spectrum, indeed. Yeah, we have also very detailed spectrum. I mean, other people also computed. So okay, so now the picture changed, and okay. So
may I ask a question before?
Yes.
If you go back one transparency.
I think it's important.
Yeah. So this left point there where you have the white dot. Yeah, this one. Can you get this perturbatively around 1 and in G?
Yeah.
Oh, sorry,
okay.
expanding around NC somehow.
And that's very interesting point, but let me see. So we found by conformal perturbation theory, naively looks like this. So it never turns. Okay, so it is monotone and diverges like this.
Because this, I mean, this diagram you draw, we have the same in the random field ON model. If where you can do an expansion around 4 dimensions and n minus nc, and nc is 2.83, something like this. It's controlled perturbatively.
Oh, okay.
You get the same diagram.
I guess the claim is here that the figure on the upper left, so this is for 2 loop, okay? So if somebody was able to push this computation to 3 or 4 loops or something like that, then we would still see this divergence, but the NC would move towards 1/2, which is roughly the numerically determined value where we cease to see this R fixed point.
That can happen. But even in that situation, we might not find, I mean, this strong disordered fixed point.
And the strong disordered fixed point, it's not accessible perturbatively for the reasons that Hirohiko has been mentioning.
Well, these pictures are, of course, all over the place. I mean, every time you have 2 fixed points, they can annihilate and disappear. So, for example, do you see that when the 2 fixed points disappear, we expect that there has to be a marginal operator? Do you see it in the transfer matrix analysis? When they annihilate, I mean.
Let me see. So, so in the, how should I say, this merge of two fixed point is observed as in the central charge landscape. So, okay, two extrema is actually merging. We don't measure a spectrum at this NC actually. Yeah.
So Slava, just to get it right, I suppose you are referring to, for example, what has been discussed previously about the critical dimension for the three-state Potts model, where critical and tricritical merge. That's what you had in mind.
Yeah, that's one example, but there are many other examples where such things happen. You know. And they always have to be accompanied by a marginal.
I see.
Singlet scalar parade.
I would suspect that you should see something like this, but you should bear in mind that making this numerics for disordered models, it's really dauntingly complicated. Hirohiko already explained to you that you have to multiply your transfer matrix 10 to the 7 times. And then you have to, so this 10 to the 7 is chosen so large that your error bar on the free energy on a cylinder with L is under control. And then you have to do it for several sizes. And then you have to extract the finite size effect. It's the perfect recipe of an almost impossible numerical problem. And so if you say in addition that you want to get such fine details at some NC that is known only approximately, I think you have the description of chaos. So I think it's very hard. But in principle, why not?
Okay. So yeah, that's an interesting point. Okay, so let me speed up a bit. So actually the dimension is perfectly matches. I mean, conformal perturbation theory and the transfer matrix are in very good agreement for this, for weak disordered critical point. Okay, so now about this strong disordered fixed point. So we have measured central charge, effective physical central charge in this accuracy, 0.4612. And we have no analytical derivation for this value. And actually, it was computed in a slightly different context by, for instance, Onika et al. So it was found in Edwards Anderson model, plus minus J random Monte. Okay, so very similar model for the spin glasses. And from the paper of Nishimori and also Ilya and Replica and Reed, this fixed point is discussed. We have no analytical derivation for this central charge, but it is known that I mean, fine structure of this critical point is some fine structure is known. Okay, and here is the plot of central charge for one parameter n against one parameter n, and at n equal 1 we have this one. So we have actually one parameter family of this strong coupling fixed point for each n. And this Nishimori line is defined by some special relation between the probability of one and the strength. So it's actually, I mean, some fluctuation of the temperature and randomness is at the same order. Some special thing happens, and this multicritical point exists. Indeed, actually, we can check this correspondence by explicit duality in the presence of disorder. Actually, we can, even in the presence of this dilution, so red represents x1 and blue represents weaker one, and then we have actually duality And so it's there to actually the random bond Ising model on the triangular lattice. So actually, if we also change the bond probability, it matches with this observation. Okay, so this is some of the fine structure of this critical point. So this is a paper by Pico and Meka and so on. So this is again the transfer matrix computations for the nth moment of 2-point spin function, and each defines this critical exponent, and so along the Nishimori lines, actually this exponent appears 2 by 2. So actually, eta 1 is equal to eta 2, and eta 3 is equal to eta 4. And they measure this critical exponent. And of course, we don't know the derivations for this spectrum. And okay, so on the other hand, if we, so this was shown by this paper by Gutzberg and it has also some supersymmetry OSP to N1 and N2M. So this at this strong disorder fixed point, symmetry is enhanced to the supergroup. So I think this is a very difficult but some good target for the Bootstat if we know how to Bootstat supergroups. Yeah. Okay, now this is quite a new paper by Delfino and Jansen and so on. Actually, so S-matrix, excuse me. So how can we? Recently, some interesting development happens in the conscious disorder ON model. So they use S-matrix to find these critical points, fixed point. So this S1 and S2 and S3 is some matrices for the particle remains in the same layer, and this S4, S5, S6 is interlayer coupling. And they found by the unitarity of S matrices, they find these 6 equations for this modulus and the phase of S matrices, and somehow they succeeded to draw this diagram, this kind of diagram. So they find as a solution, they find this weak randomly fixed point as one solution, and they also find this strong disordered fixed point as another branches of this S matrices. And now, quite surprisingly, they find also the exact value of NC, where this weak randomly fixed point and this strong randomly fixed point merges. So by transfer matrix, it's about 0.5, and the conformal perturbation theory, it's like 0.26. But very interesting, they find the exact value. That's square root minus 0.1. It's all for M-coupled. So maybe this method may be also used.
But in your picture, there was this nice smooth merger of the two curves with a kind of parabola structure, and here is just kind of intersection. What's going on?
Let me see. So in their formalism, this low fall corresponds to the interlayer disordered modulus. So you are talking about this.
Yeah, I'm wondering why is this happening not in a smooth way, this merger in their picture?
You are comparing with this and this.
Yeah. So I like your picture much better. So what's going on?
So I don't have a clear answer to this. Somehow this point looks like infinite. I mean, it's most strongest disorder in this diagram. So it's like it's like some blowing up this part. Yeah, I don't have the answer to that question. This part is somehow sent to here. think curvature does not have mean. I don't know. Curvature here.
But then that's a strong disorder fixed point, which in your drawing to the left is a capital Z. Not
yeah, indeed. Yeah. So somehow this and this are somehow jumped here, connected in this story. Yeah. Okay. So this is a current situation. Here, okay. S is somehow connected to Z in this analysis.
So they don't have the point N.
Point N. So actually for N equal 1, this should correspond to C equal, this value, 0.4612 at N equal 1. And are you talking about N?
Yeah.
Yeah, N.
If you say this is strong coupling, then it's not the crossover point, which on the left graph is shown as N, but the result of the trajectory in G. And when you go up, there's also.
I see. Oh, okay, I see. Well, let me see.
And then it's more consistent, but they don't have the unstable fixed point.
Well, look, I mean, in these papers by Delfino and Lamson, there are some very, I don't know how to qualify it. I mean, audacious, brave assumptions. I mean, they are trying to make a strike of genius, and presumably it is, but it's not so easy to compare what they are doing with what has been found numerically. I think that's more or less fair to say. So you will have to read the paper and see what you can make out of it. So the most remarkable prediction is certainly this NC. And for the rest, I'm not so sure what would be the precise way of connecting this smooth behavior that you see in the lower left corner and the other diagram that's drawn.
There may be some issues to resolve. Okay.
Yeah, or the GN, I mean, it's tilted compared to your GN plane, and that can also happen. I mean, the brown line on top could be the connection between your, well, somehow a point stood on the blue curve and the point N or something like that.
Blue curve.
But this picture could also serve like as a perfect illustration of the limitation of their method, because they claim with their method they just find all possible CFTs with a certain symmetry. But that's certainly not the case, because they make this assumption of this massless S matrices, and we don't know which CFTs have this description of this massless S matrices and which CFTs don't. So I mean, they never define, like, I mean, there's no, in the yellow book, there's no rule which says which CFTs have description this massless matrices, and they never explained it in their papers. So maybe
there's another point that's up for grabs in this series of papers by Delfino and Lamson. So they're also interested in antiferromagnetic pot models. And so there is a claim, so you know that the ferromagnetic pot model in 2 dimensions, it ceases to be second order for Q larger than 4. But using this very same construction in their paper, in their series of papers, they find that you could have presumably a second order phase transition in an antiferromagnetic pot model in 2 dimensions when Q is larger than 4, and up to a certain number that they determine analytically, something like 5 or something like that. But such models have not been identified. People have tried looking for them. So people have actually tried simulating antiferromagnets on complicated lattices to see if the 5-state antiferromagnet could somehow be critical. And the conclusions so far are not completely clear. So there is certainly something to be found out here.
Didn't Miguel have a question? I'm sorry.
Miguel?
Can you hear me?
Yes.
Not very well.
You hear me better?
Yeah. A lot better.
No, my question is indeed, I mean, what is this? What is the idea of this method? What are these S matrices? So this is on the lattice or something? And is the claim, what is the approximation involved, or is there no approximation? I mean, how are they getting these exact results?
I think there's no approximation that they impose. Yeah, about the approximation, I know. I think they don't impose anything.
So from what Jesper was saying, it just seems like it's something a bit out of the box, and it's not clear whether it's supposed to make sense or not.
Well, I mean, Miguel, you are an organizer, so arrange for these people to come and speak, maybe. What can I say?
But they won't explain. I mean, they are unable to explain this. That's the problem. I mean, I can make a comment. So the idea is that there are some CFTs which can be reached as fixed points of integrable flows. Not all, but some can. Now, we know that integrable flows, they correspond to some S matrices which satisfy Young-Baxter equations. So presumably CFTs which can be reached by integrable flows, they also have some sort of description in terms of limits of these integrable S matrices in the limit when the mass of particles goes to 0.
Mm.
So this is all very poorly understood, like on theoretical grounds. There are some vague papers by Zamolodchikov, and so this guy Delfino, he just tries to turn the crank and apply this machine in all possible situations he can find, but he postpones until the very last moment, as he told me. He first wants to work out the consequences of this machine, and then after that he will think what this all means. That's what he told me. I mean, I'm quoting him. So basically nobody understands what this means. It's just a machine that you turn the crank, it spits out some numbers, and then you make bold conjectures.
Okay.
So time will tell.
Yeah, time will tell. We proceed. So okay, so this we now turn to this M larger than 2 cases. So the basic work was done in this paper by Totsenko and Jacobsen, Luis, Pico. And okay, so the typical Hamiltonians looks like this. So it's replica symmetric. So this involves 2 layers, and okay, so this involves 3 layers. And okay, so this is I think most general replica symmetric interactions. And they found basically 3 cases. So in the number 1 is 3 decoupled Q-state pods, where only K1 is non-zero, and the possibility 2 is for the single Q to the, for instance, cubed state pods cases, where only K3 is non-zero. And they also find, this is the most important part, the fixed point with all interactions turned on. And okay, so this is a result for, I think, number 3. So this was found by conformal perturbation theory prediction. I mean, so the shift of central charge is given by this formula for generic M. And for M equals 3, it becomes this value, 2.3808. So it matches to the prediction of transfer matrices. Yeah. So it is less than decoupled 3 three-state Potts models. Shift of central charge, I mean, in this case, the flow is downhill, and the shift is very small, but yeah, it matches with the conformal perturbation prediction. Now, epsilon is the proportional to q minus 2, and to 15 for the sixth spot. So, excuse me. So here is a very simple slide for the result of Monte Carlo. And here, actually, precision is not intended. They establish in this measurement, they established the scaling behavior, and they measured, for instance, excuse me, what happens? The dimensions for this symmetric and unsymmetric combinations of this energy operator. So this is the prediction for m equals 3 of conformal perturbation theory for q equals 3, and they compares this. Prediction is not good here. I mean, agreement is yeah, reasonable, not so impressive here, but clearly establishes this scaling behavior. And now about the result of transfer matrices. So they also measure this higher operator. For instance, this combinations, epsilon 1, epsilon 2, and this replica combination, and unsymmetric one, second order and third order. And on the left side, I quote the result for results from conformal perturbation theory, like this for m equals 3, and for the odd sector, I mean spin sector, they obtain this result. And here's a table for the odd sector, and it compares to this result from transfer matrices. Okay, it agrees. So, excuse me, and yeah. And then here is a result from transfer matrix for even sector, and they identified, try to identify the subleading Lyapunov exponent to specific operators combinations, and basically this compares with this 2.08 compares with 2.1, and so 2.28 compares with 2.4 for this epsilon 1, epsilon 2, epsilon 3 energy operator combinations like this. So here, these are the results for m equals 3. And now the spectrum of m equals 3. Now this is the paper by this one, and okay. So in this paper, the explicit duality relation between this original coupling K and some duality coordinate, and it was found that the self-dual manifold has dimension integer part of m over 2, and also there was numerical result for this central charge landscape. Here, by using this duality coordinate, actually this m equal 4 decoupled 3-state postfixed point is identified exactly as a square root 3 and 3 point of this duality coordinate. Yeah, and this is downhill to the some non-trivial S4 extended 3-state post fixed point. And on the other direction, this non-critical 3 to the 4th state Potts models. Yeah. And the theoretical prediction for the shift of central charge is minus 0.0168. And okay, so it matches to precision is not high, but it matches to the measurement from transfer matrices. So even at the M-coupled is not real S4 eccentric state fixed point candidate is found. Yes.
What are you trying to achieve by looking at larger M? You're probably interested in the case, of the disordered system, so M equals 0.
Okay.
What
so
is your strategy? You would
yeah,
try
yeah. Primarily,
find
for
that
myself,
continuation, or
well, excuse me. So primarily, I myself was interested in M equals 0, but okay, but it's one very naive expectation is that if we know all the properties for the integer value of M, I know it doesn't hold, but if we know where about M equals 3, that kind of naive thing. If we know the CFTs for replica symmetric models for every positive integers and try to extract something on M equals 0. Yeah, that's one naive thing.
Well, I mean, at the time of this study, we wanted to establish that we can find these fixed points for M equals 3, 4, and so on. And then the hope was that using techniques of extended conformal field theories that we would be able to solve those models exactly. Okay, this was, of course, a very brave assumption, and we didn't succeed in doing that. Although we learned quite a lot about parafermions at the time, as I remember it, but it's a problem that's still up for grabs. I mean, these models are supposed to be unitary, and you can say many things about their symmetries. And so it seems possible that somewhere there should be a CFT describing them. And if somehow one could get analytic control over any integer M larger than or equal to 3, then you can make the analytic continuation, and then you will have solved the disordered problem at the same time. But waiting for such a progress to be made, at least maybe the community here could try to bootstrap and attain a much higher precision for M equals 3, 4, and so on. So that's the challenge that is set here.
But maybe one can also turn this around. In fact, it's interesting that you tried to. So I don't know much about parafermions, but correct me if I'm wrong. If there were parafermionic description for these theories, then it would mean, in particular, that there is some extended symmetry with respect to Virasoro, like some double symmetry. Is this correct?
That's what people tried to do at that time.
Yeah, and so,
the second proof that there is no parafermionic possible chiral algebra. So you prove a orthogonal theorem. And the idea is that you have the replica symmetry realized at the level of a spectrum, but not at the level of a chiral algebra.
Because there is a conjecture that this CFT with M equals 3, I mean, it's kind of, okay, it's a false conjecture by the lack of imagination, is that it's conjectured to be the simplest CFT with the smallest central charge, perhaps, unitary, which does not have an extended chiral algebra. Of course, so because people believe that theories, there are two beliefs. One belief is that the theories with extended chiral algebra are actually very special, and the most CFTs don't have an extended chiral algebra. But there is a problem that even though we believe that most CFTs don't have this extended chiral algebra, there is not a single explicit CFT for which it is proven. Because it's very hard to prove that I don't know, how do you prove that there is not extended chiral algebra? Maybe there is no like charge at spin 10, at spin 12, but maybe there is like a charge at spin 1000. So how do you prove this?
In this case, I think, I mean, like, it is proven in the sense that if you want to a chiral algebra has to implement at least the Z-free symmetry of the replica.
Yeah.
And I think that, I mean, I think Volodya told me that at the end, he proved that the only possible associative chiral algebra with Z-free symmetry are the ones that have been with a certain dimension of the parafermions and that it correspond to the like the first parafermion solution, second parafermion solution, but no one has this can describe this model. By the way, this model has probably a central charge which is irrational. Probably,
but we don't know.
Yeah, we don't know. But at least I think that there is a no-go theorem about the existence of an extended like chiral algebra. Okay, so there is no.
Any extended chiral algebra or just one which is constructed in terms of parafermions?
If you want to, like, the first things you want to know to do is like some currents that realize something like Z-free. Okay, because you want to realize as the replica symmetry. And I think that there is no, I mean, like at the end, if you play the game with the, you know, you have to implement, so they have to have some, you know, no locality monodromy relation between the currents, and the consistency at the end tells you that the only possible chiral algebra that do that are already being classified and corresponds to other I mean, like they do not coincide with this one.
I think it would be nice to have a discussion about that later. But, like what exactly have been, what kind of no-go theorem has been like? Is it...
Okay, this was like, you know, I mean, this was my PhD project proposed me by Volodya, and then I think that Volodya finally worked out a no-go theorem on that. But yes, I mean, we should ask to him.
Okay, so let's submit this suggestion to the organizers. Okay, so.
But this answers the question of Kai. So there are some people interested in this theory just because it's like the simplest non-solvable CFT in 2 dimensions, not exactly solvable.
Yeah, I mean, for which a solution has not yet been found.
Yeah.
I mean, there's nothing that is not solvable. There are things for which a solution has not been found yet.
Technically, they say it's the simplest irrational CFT in 2 dimensions. That's the conjecture. That's the conjecture. It would be nice to decide.
I mean, it's interesting that you can look only at unitary theories and then extrapolate with that information to a non-unitary one. This I have not read yet.
Yeah, I mean, this is a kind of dream, I mean, but yes, but at least the coupled model looks more, at least they are more under control before doing the limit. Yeah.
This is a dream machine, anyway. So, Hirohiko, maybe you.
Okay, so basically this is basically the last substantial, right? So this is conclusion. So RG flows are very much controlled in 1 minus m expansion, like u minus 2 expansion in 2 dimensions. And both m equals 0 and m equals 3, 4, 5 have interesting features. And for m equals 0, I think the presence of non-perturbative fixed points, that is actually the extension of the Nishimori universality class at n equals 1, k equals 2 is very, very interesting and important. And perhaps awaiting, maybe it's a not a problem for immediate future, but it might be interesting target for the supergroup Bootstat. For instance, some spectrum is also measured in rather good accuracy at n equal 1. And also this derivation, any derivation, analytical derivation of this effective central charge 0.4612 is very interesting. And okay, so S-matrix method, I think it was impressive. It can find NC that was not found in conformal perturbation theory. Okay, it's about m equals 0. And about this large M, okay, the spectrum has been studied in conformal perturbation theory, and then many detailed numerics exist. So it's good Bootstat target, I think. And my one comment is for large M, this interlayer coupling becomes very weak. So there would be something like 1 over M expansion. And it might be interesting to consider the model at M infinity, like spherical models. So if I compute the central charge there, actually, this is exact. Correction, higher order correction, I think it will vanish. And for Q equals 3, it's 1 over 125. And for Q equal 4, its shift is 1/8. And some peculiar feature is this shift is very small compared with M, order of M. Yeah, that's yeah, indeed for large M, it is okay because qualitatively okay that shift is small because coupling is weak. But it's very, very small, I think. For instance, this for non-perturbative fixed point, we have finite shift, but for this kind of weak disorder fixed point, central charge shift is very small. That's is something to be understood, I think. Yeah. Okay, that's all that I want to say. Thank you.
Thank you very much, Hirohiko. So we have time for further questions.
May I ask something about the Nishimori slide? So I just wanted to clarify, I may have missed it. So your model, you had some distribution of the bond strengths for your Xij, right? So does that distribution allow for a spin glass in your model? Spin glass?
Yes, it actually contains spin glass point if we do dual transformation.
So then you should have all this. So this phase diagram with the Nishimori line and everything
yes. This is
should be your model should be really in the same class. You should have the Nishimori line and Nishimori point. Is that the claim?
Yes. Okay. So it can actually tune to the Nishimori point also. But we find away from Nishimori, exactly the spin glass point, we also find the same universality class. It's connected, I mean, by the RG flow.
Well, but okay, so let me try to understand this. So you had this parabola-like thing, right? For n equals 1, you had this strong disorder fixed point. And my feeling is that true that you identified with the Nishimori point?
You mean this?
Yeah, this
this curve. Okay, so at n equal 1, I believe that. Yeah, I mean, there is strong evidence that it corresponds to the Nishimori multicritical point.
Right.
Yeah.
So then, okay. So what I'm trying to say is that in the phase diagram on the right, you have 3 fixed points, right? You have 2 critical points and 1 multicritical point.
Mm-hmm.
So you have a clean point, you have a Nishimori point, and you have the spin glass transition point. Mm-hmm. So do you have access to the spin glass point? Do you know anything about it?
Well, access to the Spinger's point. Well, let me see. So zero temperature fixed point is another interesting point. So it forced to, yeah, this diagram is different for this originally different for models, but it has qualitatively the equal similar behavior.
No, I'm talking about the fixed point at 0.12 at the t equals 0 line.
Ilya, you're talking about t equals 0, I think.
Yeah, exactly. Yes, that's what I'm
and in Hirohiko's phase diagram, there's also something going on at infinite disorder. So yeah, stop. No, the other one. Oh yeah, sure. Yeah, here. Yeah, Z. Okay, so there is something like infinite disorder. So maybe there's a possibility that this corresponds.
Yeah, indeed.
Yeah, no, the reason I'm asking is that almost, I mean, pretty much nothing is known about that fixed point. And so this would be very interesting to
so in the case of in the Q state random bond Potts model, you can actually solve the infinite disorder fixed point analytically. This was something that I did with Giancardi in my thesis. But here in the ON model, it's a bit different. So you can actually compute for the Q state Potts model at any Q, and infinite disorder you can compute, for example, the effective central charge analytically. Actually, maybe I could say here also that it's kind of fascinating that in a model here with strong disorder, but positive couplings, you can find the same fixed point as you find at the Nishimori point with coupling constants of either sign. So it shows quite clearly that there's some kind of universality to random fixed points. And that maybe frustration is not such an important ingredient to attain strong disorder.
Yeah, I mean, the n equals 1 case is special because it maps to free fermions, and then it's one of the AZ classes. This is class D. So that may explain this universality. Right? I mean, this is just a fermionic problem, free fermions.
So, are there any other questions?
So you're also saying if you take a self-avoiding polymer and you put it in this order, there's only the strong coupling phase.
So polymer in disordered environment corresponds to this, and flow is one way, I think. Yeah, this story. So this
there was I don't know which dimensions, but there is a debate whether if you take a Gaussian polymer, it will always go to the deepest minimum of the potential, and it will just go down there. So, but if you have self-avoidance, this artifact, it cannot just go to one point. So if you take self-avoidance, there was always a discussion whether this makes a physical fixed point, which is not just compactified somehow. I thought it was open, but maybe.
So the same question you are saying could be asked in 3D. 2D, indeed, it shows that there is no fixed point.
Well, no, but they don't show there is no fixed point. They show there is no perturbative fixed point. There's a strong coupling fixed point. The question is the strong coupling fixed point, a fixed point where for instance, all the monomers go into one side, which they can't, but maybe a compact object, or is it still a critical object? So this is not a question I think they can answer.
No, but they did Monte Carlo transfer matrix. The strong coupling fixed point is just a massive theory, or it's not a CFT, is it? I missed this. I thought Z was just some massive theory.
That's a question for Hirohiko, I think.
Matrix theory.
No, massive theory. Z is not a CFT, is it?
That might be a CFT.
In the random band patch model, it is.
Yeah, I see. One can compute analytically the effective central charge for systems.
So my naive expectation is that it might actually be, but it's hard to study.
Yeah, this one.
I mean, for other theories, I also see running to strong coupling, but then somehow everything rearranges and then it becomes a nice perturbative fixed point. So with scale invariance, which is not massive.
Why is it hard to study? Can you explain why is it hard to study?
Yeah, sure. So in the numerical simulations here, we are having a system with two kinds of couplings. One coupling constant that tends to infinity and another that tends to 0. And then you want to throw on top of that, you want to throw ON loops. ON loops, they have to form loops, okay? And they have to pick up as many of the strong bonds and as few of the infinitely weak bonds as possible. So it's a kind of a problem of combinatorial optimization.
I see.
And so for that reason, it's difficult to study. We tried actually at that time, and I think there is still room for some improvement. So we are running a bit out of time, I think. So if there is no urgent question, I think we should thank Hirohiko for this very nice talk.
Thank you so much.
And we will resume in about 5 minutes. People here will go and have coffee, and then we'll resume with the next talk.
Yeah, so let's not resume. Yeah, so 5 minutes. Let's make a break because we need to deconfine.
So you propose more than 5 minutes?
Yeah, I
think we should ask. Maybe we should ask Amnon. Amnon, what do you say?
I'm flexible. Go have coffee.
Okay.
Okay, let's resume at 11:40.
Okay.
11:40.
Good.
Okay, thank you very much.
Okay.
I think you should stop the recording and then resume it.